Hello everyone, and welcome to CUSP. Welcome to the Urban Computing Skills Lab. We hope it will help you to get a refresher on the important skills and capacities that you might need to be successful in the Urban Informatics program. My name is Stanislav Sobolevsky. I'm a faculty here at CUSP. I'm an urban data scientist, a mathematician by training, and I'm delighted to be one of your instructors. I'm looking forward to have some good time talking to you about probabilities, some aspects of analysis. So basically, why do we care about the probabilities? Since you joined the program, you should be pretty much aware of the fact that data science is a big deal for our cities, which see an increasing availability of different sources of big data created by different aspects of human activity. However, data science often has to deal with uncertainty, because data is often inaccurate. Sometimes it's missing, sometimes it's inconsistent, and quite often, whatever prediction we come up with, people certainly won't follow this prediction, and urban systems as a whole, as a complex system, won't follow it either. So we have quite a bit of uncertainty here to deal with. However, the theory that deals with uncertainty is not uncertain by any means. It's a pretty robust and rigorous mathematical theory, which we call theory of probability. So, what is the probability? We're so used to this term that whenever we say that the probability of having rain today is going to be 10%, we often don't even realize what's behind those words. What does it actually mean? What's behind the digit? So, we're going to talk about the concept a little bit more, because actually there are two approaches to it: frequentist and Bayesian. When I say there are two approaches, I don't mean that one is better than the other, because if that would be the case, then certainly a long history of the subject would already replace it with the best one. So there are two, and they're pretty much complementary. One could be used in one context, the other complements it in the other context. So it's good to be aware of both and employ them whenever they fit better, whenever they suit our needs better. So we start from a most sort of common and basic one, the frequentist approach, which pretty much means that whenever we talk about probability of event to happen, we talk about the frequency, how often this event happens among all the trials that we make. So for example, if we are tossing a coin and our event is coin coming heads up, then the probability is going to be a frequency of this happening. And if we toss the coin 100 times, for example, and if we see heads 51 times, then the probability is pretty much 51 divided by 100. It's a little bit above 0.5. So that's pretty intuitive, pretty simple, pretty easy. However, this has a major drawback, because it largely depends on the sample of observations we have so far. So what if the sample is small enough? What if the sample is incomplete? Or maybe what if we don't have any observations at all? Say, what if we just toss the coin twice? And in both times, it comes heads up. Does it mean that the probability of this event is 100%? Well, formally speaking, based on the sample of observations we have, that's the case. However, we clearly understand that it's not really practical. On the other hand, sometimes we might not even have those observations at all. Say, what if we wondering about the probability of a major hurricane stronger than Sandy hitting New York City next year? We never saw such hurricanes in the recent history, right? So we don't have any observation history here. We can't judge. From a frequency standpoint, we're just stuck. However, of course, if we know something about the process in the atmosphere, we know something about statistics of the hurricanes, we know something about their most common paths, we probably can make a guess. But this already goes beyond the regular frequentist approach. That might well involve the Bayesian thinking. So what is that? From Bayesian standpoint, the probability of the event is our degree of confidence that this event is going to happen. which certainly varies from 0, we are pretty sure that the event would never happen, to 100%, we're absolutely certain that the event will happen for sure. In that case, we're talking about the probability of the event conditional to our prior beliefs about this event, about the event itself, about the context of this event, and in general about our prior knowledge of what's going on. So if we're talking about the coin, and if we know that the coin is fair, given our knowledge, we would say that the probability of coin going heads up is 50%, because it's equally probable that it goes that way or that way. That's our belief about the coin. If we are told that the coin is not fair and someone made some tricks with it, then perhaps your beliefs are different, and then your probability might be different. But given the belief about having a fair coin, the probability is going to be 50%. So for that purpose, we don't need any observations at all. We don't need to throw the coin. We just know from the beginning that it's going to be 50%. And then, based on some probabilistic rules and assumptions that we'll be talking about just in a few minutes, you can derive more complex probabilities of more complex events to happen. So from the Bayesian standpoint, actually the good thing about that you can talk about pretty much any events that you might imagine. For example, there is a joke about like corrupted logic. Like, what is the probability of meeting a dinosaur on the street? And the joke says that, well, the guy says, well, it's probably 50%. Why? I mean, how could it be 50%? Well, I mean, I either meet a dinosaur, either I don't. It's going to be 50% then. So that's a joke. That's a funny thing. But from the Bayesian standpoint, that's not a joke anymore. That's a pretty robust conclusion in case if you don't have any prior information about dinosaurs, streets, and whether they are actually running around there. So if you have no prior belief, no prior knowledge, or the Bayesian scientists call it uninformed prior, then yes, your probability of meeting a dinosaur on the street is pretty much 50%. You can meet it or not. Frequentists would probably need to spend quite a bit of time on the street looking for dinosaurs, not meeting any, and then concluding that it's 0. Because I spent 100 hours, none of those, I meet any dinosaurs, so probability of meeting a dinosaur during a specific hour is 0 from my frequency standpoint. On the other hand, Bayesian scientists, if given information that the dinosaurs died long ago, he or she will tell us the same thing, the probability is 0. But for that purpose, we need some prior information, prior knowledge. So that's pretty much the difference between frequentist take and Bayesian take. Going further, it won't be that much of a difference what kind of take we employ, what kind of paradigm we stay with, Bayesian or frequentist. The basic rules of probabilities are pretty much the same. However, having those two paradigms in mind will help us deal with more complex things, more complex scenarios, when we need to employ some non-conventional thinking. So far we've been talking about the simple event, like which can either happen, either not happen. But quite often, the events have a complex nature. You might think of a certain sample space of possible outcomes when an event is one of the outcomes happening. For example, imagine you're drawing a domino tile, and your event is having equal values on both ends of the tile. So in this case, the elementary outcome of your experiment is one of those 28 tiles. You can draw them with the same frequency, while the event that interests us is drawing one of those. One of those tiles which have equal values on both ends. So that's our event. And if the frequency of drawing each specific tile is equal, then we have 28 tiles. We draw each specific one with a frequency 1 divided by 28. Then the frequency of having this event to happen will be 7 tiles of 28. 7 divided by 28 is going to be 1 divided by 4. We end up with 25% probability of drawing the tile that satisfies us. Generally, there's a good visual approach to deal with such complex events. We visualize the sample space on a line, on a plane, or in a three-dimensional space if it's too complex, where the different points are different possible elementary outcomes. And the event is a domain in this space. It's a set of points, which means that event actually happened. The set of satisfactory elementary outcomes, which form an event. So in this case, the event A has 9 possible elementary outcomes in it out of 18 total possibilities. And the rest of the domain is called a complementary event, not A. It means that event A didn't happen. So if we are here, here, or here, we're not inside the domain of event A. So we're inside the complementary event, not A. Obviously, the probability of the complementary event is just 1 minus probability of the event A. So for event A, we know that it encircles 9 of 18 possible elementary outcomes. So this probability is going to be 9 divided by 18 is going to be 50%. And the probability of the complementary event, not A, is going to be 50% either. So it's 1 minus 50%, 50%. So this type of visualization allows us to deal pretty intuitively with a complex probabilistic phenomena. For example, let's imagine that we have actually 2 events on the plane. One is event A, and the other one is event B. For example, imagine that, again, you're drawing a tile, domino tile, and one event is that you got a tile with a total weight of numbers, even, with an even weight, even sum of numbers on both ends. And the other event, B, is that you draw a tile which contains 1 6, at least 1 6. So those events can certainly fly together. You can draw like 6 and 6. It's going to be even, and it's going to contain 6. So elementary outcome might belong to both events, or it may belong to just one. So you draw 2 4. The sum is even, but doesn't contain any 6. So in this case, it belongs to A, but doesn't belong to B. And actually, this picture is good to illustrate 2 basic operations with the events. One is union. The other one is intersection. So the union of 2 events is the event that basically unites both of them. It includes all the elementary outcomes that form any of the 2 events. So it means that we draw a tile which either has even weight or contains 6. On the other hand, this domain, which is the intersection of 2 events, contains those elementary outcomes that satisfy both events. So you have at least 1 6 here, and the sum should be even. So just from this simple picture, it starts being sort of obvious how to deal with the probability of union and probability of the intersection. For example, imagine if you want to have a probability of a union. What is it going to be? It's going to be the probability of the first event plus the probability of the second event, but there is one problem with that. You count intersection twice. So in this case, you need to subtract the intersection. So it's going to be probability of A plus probability of B minus probability of those 2 events happening together. And that's going to be the probability of at least one of the event happening, probability of the union of the events. In a similar fashion, if you're wondering about what is the probability of both events not happening, so what is the complementary event to the union of those 2, then you can easily see that that's going to be the intersection of the complementary event to A and complementary event to B. So if you need to make sure that none of those events happened, so your you're dealing with this domain where none of them happened. Then this domain is an intersection of the complementary event to A, if A not happening, and complementary event to B, B not happening. This is why we have this type of formula. Okay, so another important particular case that we need to consider, because it has multiple practical applications, is the so-called case of independent events. Let's not confuse them with mutually exclusive ones. It doesn't mean that those events cannot happen together. They pretty much can, but they happen independently in a sense that they actually exist in independent sample spaces. What do I mean by that? Let's imagine an experiment when we toss two different dices. And we're wondering what are the odds of getting both 6. In this case, I can visualize the sample space for those two events on two separate lines. I can imagine them intersecting, but it doesn't really matter. What matters is that they are separate. The sample space for the first dice contains 6 elementary outcomes. One, 2, 3, 4, 5, 6. And what satisfies us is getting 6. The elementary space for the second dice, which I am rolling, also contains 6 different elementary outcomes. 4, 5, 6. And what interests us is getting here 6, 2. Now, if you imagine the sample space of rolling both dices, you pretty much have the direct product of those two sample spaces, if you know what I mean. If not, don't worry, that's just the grid, where you have 6 options for the first event and 6 options for the second. On this grid, you have 6 by 6 possible outcomes, 6 for the first dice, 6 for the second dice. And the satisfactory outcome means that both of the events should happen, so we should be here. So we only have one satisfactory outcome out of 36. So the probability of this happening is 1 divided by 36. Generally speaking, if the first event, say, has 8 satisfactory outcomes out of the total x, total is x, here you have A. And the second event is say, has y satisfactory outcomes. Oh, I'm sorry, not y. And this convention is going to be B satisfactory outcomes out of the total y. Then those two events happening together have A multiplied by B satisfactory outcomes out of the total space of opportunities being x multiplied by y. So in this case, as the probability of the first event A, was A divided by x, probability of the second event, B, was B divided by y. Okay, then the probability of those two events happening together, event A and event B, as we know, is A multiplied by B divided by x multiplied by y, which pretty much equals to A divided by x multiplied by B divided by y, while this is the probability of the first event and this is the probability of the second event. So what we have in the end is the probability of two independent events to happen together is the probability of the first event happening multiplied by the probability of the second event happening. So we'll go to the formula on the board. And that's actually a pretty handy formula, because in many cases we deal with independent events. For example, what is the probability of having 10 heads in a row when tossing a coin? Probability of having one head, like one satisfactory outcome, one head is 50%. When you need to get it 10 times in a row, you basically need to multiply this 50% by 50% by 50% 10 times. Those events are independent. So the outcome of the second tossing is not really dependent on the outcome of the previous one. At least we believe so. So the coin doesn't become biased while we toss it. In this case, the probability of getting 10 heads in a row is going to be 0.5 power 10, and that's already 1 divided by 0.24. It's approximately 0.1%, so 1 of 1,000. And in many similar scenarios, we can successfully employ this formula. However, there is one limitation, which I might want to tell you. So remember our experiment with drawing a dominant tile, which need to have same values on both ends. This event had a probability of 25% because we had 7 satisfactory outcomes out of the entire option space of 28. However, if you are wondering what are the odds of drawing first and then second tile so that both will have equal numbers on the ends, saying if it's going to be 25% by 25% would actually be wrong. Why that's the case? Let me get back to the tile space. Let's imagine that I took one tile and it was out of this satisfactory set. And now I'm about to take the second one. Taking the first satisfactory tile was the first event with a probability of 25%. That's what we know. But now, once I took one, let it be here or here, doesn't matter. I'm left with 27 tiles. And the remaining part of the satisfactory ones is only 6. So now, my probability of taking a satisfactory tile will be not 7 by 28. It will now be 6 of 27. So then the probability of drawing 2 satisfactory tiles, 2 tiles with the same numbers on both ends, will be 7 divided by 28 for the first one, and given that we got the first one like that, 6 divided by 27 for the second one. So we end up having a probability of 1 divided by 4 multiplied by 2 divided by 9. So it's going to collapse to 1 divided by 18. Instead of 1 divided by 16, which we will get if we just say 25% by 25%. So that's the difference. And the reason why we were not able to apply the simple formula of for the independent events is that those events are not independent. Your odds of getting the second tile with equal numbers depend on the fact, are affected by the fact that you already got one tile like that from your entire set of tiles. This is the limitation of applying this formula. Just remember that not all of the events you encounter are actually independent. So if they are independent, go ahead, apply this formula. If they are not independent, think twice and consider them appropriately. Okay, so the events that we considered so far were sort of binary, meaning that event might either happen or not happen. Here, I'd like to generalize it a little bit, considering events that might have not 2 but more than 2 possible outcomes. Specifically, let me consider a discrete random variable, which value we're uncertain about. So far, considering events, we were dealing with binary random variables, meaning that it can be 1 or true if event happened, and it might be 0 or false if event not happened. Now, let me consider an arbitrary random variable which possible value belongs to a discrete set of possible outcomes S. Let it be like 1, 2, etc. m, where m is the total number of possible outcomes. For example, imagine I'm rolling a dice. In this case, the set of possible outcomes contains 6 possibilities. I can get 1, I can get 2, I can get 3, I can get 4, 5, 6. I can have 6 options. And each experiment leaves me with one of them. So instead of getting 1 or 0, happened or not happened, I'm getting one of the 6 possible outcomes. In this case, what we need in order to describe this random variable from a probabilistic standpoint is basically a following decomposition of the random variable into binary events. We can consider a probability of each outcome happening. What is the probability of having 1? It's 1 divided by 6. What is the probability of having 2? Again, it's 1 divided by 6. What's the probability of having 6? Again, it's 1 divided by 6. So once we know the probabilities of all the possible outcomes to happen, we pretty much know the behavior of this random variable. And in this case, we say that we have a probability distribution for this random variable. Let us consider an example. Again, let's get back to my favorite board of domino tiles. And let's consider a following random variable. We take a random tile, and the value of the variable is going to be its weight, which is the sum of the values on both ends of the tile. So in this case, I actually have 12 possible outcomes, because the weight might vary from 0, both are zeros, all the way to 12. Both are 6. So 12 is the max, 0 is the min. So I actually have 13 possible outcomes here. So now let's consider what is the probability of having 0. If we have 0 as a total weight of the tile, it means that both ends are 0. Both ends are empty. So that leaves us with one possible choice. One single tile out of 28. So the probability is 1 divided by 28 then. Probability of having the weight 1 is the same, because I only have one single tile which totals at 1. 0, empty, 1. Again, it's 1 divided by 28. But the probability of having weight 2 is already higher, because I actually have 2 tiles like that. Right? One is here, 1, 1, and another is here, empty, 2. I have 2 tiles out of 28. So my probability is already 1 divided by 14. In a similar manner, the probability of getting 3 is again 1 divided by 14, because I basically have, again, 2 options, 1, 2, and empty 3. Probability of getting 4 is 3 divided by 23, because I already have 3 options. I may have empty 4, 1, 3, and 2, 2. For 5, I again have 3 options. For 6, I have 4 options. Which are they? Well, empty 6, 1, 5, 2, 4, 3, 3. I have 4 options. Going forward, if we want to figure out probability of s equals 7, 8, etc., you can do it by hand as well. But also, you can just notice that the probability is actually symmetrical. So probability of having a weight 6 plus k, for example 7, is the same as probability of having the weight 6 minus k, 5. Or probability of having the weight 8 is the same as probability of having the weight 4. Why is that the case? Because we can basically just flip the numbers. You can replace 6 with empty, 5 with 1, 4 with 3, and that will pretty much reverse the entire picture. I mean, you can trust that, or you can just do your due diligence, and you will see that indeed the probability of having 7 is the same as 5, probability of having 8 is the same as 4, and so on. But anyway, what we end up with are the probabilities of having each possible outcome. We can visualize them as a bar plot. So here is the possible outcome, k, going from 0 to 12, and here is the probability. I actually haven't normalized the probabilities here, so I just say 1, 2, 3, 4, just divide it by 28, and you'll be fine. So this is called the visualization of the probability distribution, and the cumulative probability, if you sum up everything here, will be 1, because the total probability of having something, no matter what, is of course 1. You always have something. But it might be 0, it might be 1, it might be 2, it might be 3, and this is the way how this plot shows you how this entire probability 1 is distributed among different possible outcomes of the random variable. So this is why it's called probability distribution. Now let's consider a few quantitative properties of the random variables so that we can deal with them efficiently. The most common one, the most basic one, is the mean. What it is basically the weighted average of all the possible outcomes. So you take all the possible outcomes k, and you weight them by the probability of each outcome to happen. So the more probable is the outcome, the higher is the weight. For example, if only one outcome has a positive probability and all the other outcomes are pretty impossible, then all the outcomes have probability 0, one outcome have probability 1, and then your mean equals to this only possible outcome. If, for example, you're flipping a coin, like if it goes heads up, your outcome is 1, if it goes tails, your outcome is 0, and the probability of both outcomes are equal, 50%, then your average, then your mean is going to be 50% multiplied by the value of the first outcome plus 50% multiplied by the value of the second outcome. So it's going to be 1/2. So you toss the coin, one outcome is 0, another outcome is 1, average outcome is half, of course, because you have either 1, either 0, half is what you get in the middle. Generally speaking, you just take all the outcomes and weight them by their probabilities. And that's called mean, or another term is mathematical expectation. The other important quantity is the variance. Variance shows you what is the average, what is the mean of the deviation from mean. Like it sounds a little bit cumbersome, but let's take a breath and think of that. So mean is important. It shows you what is the average outcome you should expect. But besides the average outcome, what else you want to know is how diverse the outcomes might be. Because, I mean, one option here to have the average outcome half, you can, with the same success, get it by just having the only possible outcome half. It's always half, and the mean is half. Or you can have sometimes 0, sometimes 1. The average, again, is half. Or you can have sometimes -2, sometimes -1, sometimes 0, sometimes 1, sometimes 2, sometimes 3, and again your average is going to be half. So all those random variables will have the same average half, but they're pretty different. And what you want to know is how much variance should you expect in the variables. And that's what this quantity shows. For each outcome, it looks at how different this outcome is from the average, and it weights takes square of it, and it weights those square differences by the probability of the outcome to happen. So you take outcome k minus mean mu square, because if the outcome is bigger, then it's higher than mu. In terms of deviation, it's pretty much the same as if the outcome is lower than mu. So you take squares so that positives and negatives lead to the same outcome. And then you average all of those values by the probability of each outcome to happen. And that gives us another important quantity, the variance. Sometimes, and actually quite often, we consider square root of variance because we kind of were considering squares here. Now just getting back to the original scale, we take square root of the result. Square root of variance is called standard deviation. And that's a third important quantity which we might want to remember while dealing with random variables. Finally, there's an interesting formula. I won't prove it, but actually the proof is quite easy. You can try it yourself if you want. If we want to know what is the average, what is the mean for the square of the random variable, or what is the square of the random variable? It's basically the variable which takes the value k square if x takes the values if x takes the value k. So that's the random variable. So its average won't be mu squared, but it will be actually mu squared plus the variance. It's a very interesting formula, and I strongly encourage you to give it a try. Maybe you can prove it. If not, we can certainly talk once you come here, or just shoot me an email. We can talk about that too. But I hope you will have some fun proving it. It's actually an easy one. Now let's conclude with mentioning a few classic sort of standard random variables that we often encounter. One is so-called Bernoulli random variable, which we're already quite familiar with. That's flipping a coin. That's basically the binary event. It has two possible outcomes. One, which happens with the probability p. It might be 0.5 if the coin is fair, or it might be something else if the coin is unfair. So what does it mean to mention p here is that actually this random variable depends on the probability p. So probability p is a parameter of the random variable. In this case, we get 1 with the probability p, and we get 0 with the probability 1 minus p. Let's compute the mean. Just a simple exercise. What is that? So we have two possible outcomes, right? 1 and 0. Outcome 1 happens with the probability p. Outcome 0 happens with the probability 1 minus p. And this is going to be our mean. We weight the outcomes by their probabilities. The total is p. So the mean of the Bernoulli distribution, the mean of the Bernoulli random variable, is p. And the variance of Bernoulli random variable, if we care about variance now, well, let's see. Again, we have outcome 1. In this case, the deviation from the mean is 1 minus p square, and the probability of this is p. Plus, if we have outcome 0, then the deviation is going to be 0 minus p square, and the probability of that is 1 minus p. So what we end up with is 1 minus p square p plus p square 1 minus p. How to deal with that? Well, we can take p 1 minus p and see what we are left with. Here we are left with 1 minus p, and here we are left with p. Those two p's cancel each other. We end up with p multiplied by 1 minus p. That's going to be the variance of the Bernoulli random variable. And then the standard deviation is going to be square root of that. So we just consider the Bernoulli distribution for the random variable. And let's consider another one closely related to it. That's the binomial distribution. The binomial distribution basically tells you what is the chance of getting a certain number of positive outcomes out of n trials of the Bernoulli random variable, or actually a random event. So imagine you have a random event, like you're flipping a coin, and the odds of getting it heads up is 50%, are 50%. Now you're questioning yourself, like after you flip it 10 times, what are the odds of getting exactly 5 heads or exactly 5 tails? You know that in each trial, it's 50%. Now, what is the chance of getting exactly 5 positive outcomes? That's what Bernoulli, that's what binomial distribution actually tells you. So, if you make n trials, and you are questioning yourself, and in each trial, the chance of the positive outcome is p, then what is the probability of having exactly k positive outcomes? And this probability is going to be p power k multiplied by y minus p powered n minus k, and multiplied by this weird number, ck of n, which actually can be expressed through factorials, if you remember what factorial is. Actually, if you don't, then it's just the product of first n positive integer numbers. So like, for example, factorial of 5 is 1 multiplied by 2 multiplied by 3 multiplied by 4 multiplied by 5. It's going to be 120. And the funny thing about factorial is that it grows pretty quickly. Like, guess how big the factorial of 10 is, unless you don't know that yet. You can try it, and it's actually going to be 3 million. And factorial of 20 is going to be billions and billions. So factorial grows pretty quickly. Now, c of k from n is factorial of n divided by factorial of n minus k divided by factorial of k. So, and those are the probabilities. You can check that if you sum it over all possible k's, and k can be from 0 to n, since you have at least 0 positive outcomes, you can have negative number of positive outcomes, and you can have the most of n positive outcomes because the n is your total number of trials. So if you sum this up over all k's from 0 to n, you will figure out that the total probability is, of course, 1. So that's the binomial distribution. Another example of the classical discrete probability distribution. Oh, and actually, let me finish with the binomial case, because I also need to tell you what is the mean and what is the standard deviation here. The mean, not surprisingly, that's the probability of the possible positive outcome multiplied by the number of trials. So if, for example, the chances of getting the coin heads up are 50%, and you try it 10 times, then on average, you will have 5 out of 10, which is sort of understandable. Generally speaking, you need to multiply the probability of the positive outcome in each event by the number of your trials. And that's going to be your average for the binomial random variable. And the standard deviation is like that. It's square root of n multiplied by p multiplied by 1 minus p. So, so that's the binomial distribution. Now let me show you another example, the Poisson distribution. That's a slightly different setting, and it has something to do with the sequence of events happening with a certain fixed frequency. You don't have any specific amount of trials. What you know is that specific event of interest happens with a certain frequency. For example, imagine you are a firefighter, and you know that on average, the fire in this area happens twice a day. So the probability, then the frequency of having a fire each day is 2. And now what you're questioning yourself is what are the chances that the fire will happen more than like 4 times? Because you only have 4 squads. They can only respond to 4 fires at the same time. So if you have 5 fires, even though on average it happens twice a day, sometimes you might have bad luck and it will happen more than that. So now, if you only have 4 squads, what are the chances that those 4 squads won't be able to answer the next call? So what is the chance that you will have at least 5 fires in the area? That is what the Poisson distribution actually can tell you. And it tells us that the probability of having exactly k events happening over the unit of time, if the frequency of event happening over the unit of time is lambda, is going to be exponent of minus lambda multiplied by lambda power k divided by k factorial. And an interesting property of the Poisson distribution is that its average equals to its variance. I mean, it's sort of maybe it's an occasional coincidence, but certainly it follows from the formula of the Poisson distribution. So in both cases, there's going to be lambda. That's the property of the Poisson distribution. So now, having this formula, you can compute the probability of having 0 fires, no fires happening, everyone's relaxed, probability of having 1 fire, 2 fires, 3 fires, 4 fires, and then the probability of having 5 fires or more will be 1 minus sum of all those previous probabilities. I won't do it right here, but you can do it on your own if you're really interested about the fate of this firefighter. Actually, not the fate of the firefighter himself, but the reliability of the system I just described. So this is it with the random variables. The only thing I wanted to mention at the very end of the lecture is one more concept about the probabilities. That's the concept of correlation. So let us talk about the concept of correlation. Imagine that something's happening, and we have 2 observations, x and y. And we're wondering how related or unrelated they are. So let's imagine x as one random variable and y as the other random variable. And they're happening in the same sample space, same sample space of elementary outcomes. So imagine that for each outcome, we visualize the values of x and y. We visualize it in the coordinate system of x's and y's. So for example, here, it happened that both x and y are pretty low. Here, it happened that y is pretty high, it's almost 2, while x, well, it's high too, but not maybe that high. Or here, x is high, but y is actually pretty low. So now we're questioning ourselves, what is the relation between x and y? The way of quantifying this relation is the following. So first, let's consider covariance. Covariance is actually the average of the products of deviations of x from average value of x and y from average value of y. What's the meaning? What's the sense behind that? So this product is positive each time when both x and y are higher than average. And it's negative if one is higher than average and the other one is lower than average. So if we believe that x and y are related, we might think that if one is high, the other one is high too. If one is low, the other one is low too. This means that this product will usually be positive. And the covariance, this way, will be positive too. On the other hand, if x and y are in inverse relation, so if x is high, y is low, and vice versa, then this product will often be negative. And covariance this way will be negative too. But finally, if you look closely on that, you will notice that actually covariance pretty much depends on the scale of x and y. So if x and y's are like between 0 and 1, probably you will get something of that order of magnitude. But if x and y's are millions or billions, you will get covariance pretty high too. So if you want to judge on the degree of relation between x and y based on covariance, it might be hard because it also depends on the scale. Now, if you want to normalize it by the standard deviation of x and standard deviation of y, you pretty much get rid of the effect of scale, and this leads you to a definition of Pearson's correlation coefficient. This correlation coefficient is normalized. It's always between -1 and 1, and it tells you pretty much how related or unrelated, linearly related or unrelated, the x and y are, the variable x and y are. If it's close to 1, the relation is close to linear. Or if it's close to -1, it's also linear, but it's just the inverse relation. So the higher is y, the higher is x, the lower is y. On the other hand, if it's close to 0, it means that there's pretty much no relation. So x might be above average, while y is below average, or they might be occasionally both above average, both below average, and all those cases are just mixed up. And this will leave you with correlation coefficient somewhat around 0. So that's a pretty powerful metric. So in many cases, you can use it to figure out whether events are related or not. However, one thing to remember here is that correlation doesn't actually mean causation. The fact that you see me outside with an umbrella every time when it rains doesn't mean that it rains because I'm taking an umbrella. Well, occasionally it means that I'm taking an umbrella because it rains. However, the relation might be even more complicated than that. I might not know whether it's going to be raining or not, but I'm seeing weather forecast, and that's why I'm taking an umbrella. So I'm taking an umbrella not because it rains because I don't know whether it's going to be raining or not. I'm taking an umbrella because I see weather forecast, and weather forecast shows rain because rain is actually expected. So you might have common cause for those two events. And it doesn't mean that one is the cause or consequence of the other. So just make sure that you don't mix those two things, correlation and causation. If you see that two events are related, it doesn't mean that one is the cause for the other. It just means that there might be a causal relation between them, or they just might have a common cause, which we do not observe currently. Finally, let's consider an example. Let's consider prices of houses across New York City. And actually, as you might know, or if you don't know, then I tell you, that's a publicly available data. You can easily download the data about all the housing sales that happened in New York City and the neighborhoods, and you can see what were the characteristics of the houses and what was the price for which the house was sold. I mean, of course, you don't have the name of the person, the name of the owner, the name of the future owner, but you have the parameters of the house pretty much. So now let's see how the price is related to the size of the house. This is the simple Python code that actually does the magic, and here is the result. So x is the size of the house in square feet, and this is the price. So certainly the bigger is the house, the higher is the price. I mean, it's not a linear relation, so sometimes pretty big house might be relatively cheap, or pretty small house might be on the higher side in the price. But if you compute the correlation coefficient between those two quantities, you will get it 92%. 92% meaning that it's pretty close to a linear relation. Indeed, you see that the correlation is pretty strong here. So correlation coefficient is quite an important metric, which you can use for an initial exploratory analysis of whether there is some relation between different quantities. It's not the ending point. Once you have the high correlation coefficient, you still need to be aware that it's not a causation, and you need to figure out what is the cause for this relation that you observe. Also, if you have a low correlation coefficient, it doesn't mean that the quantities are not related at all. It might be the case that the relation is not linear. It's actually something more complicated, and that's why the linear correlation is not there. But there might be some other relation, maybe quadratic function or something like that. But the first test, or whether something is there, is just to quantify, is just to compute the correlation coefficient. So that's a pretty powerful tool. So I hope you enjoyed that. I hope you enjoyed the introduction to probabilities. Next lecture we'll dive deeper into the topic, and we'll have some real-world examples of how those concepts can be applied. And we also have quite a few other topics to consider. So thank you for your attention, and good luck.